In this video, we discuss learning outcome number 3 for lesson 9.2, which is about testing a claim about two means with sample data collected from two independent samples using the critical value method. Here we assume that the population standard deviations are unknown, and we are not assuming that those population standard deviations are equal to each other. The rationale behind this method was discussed in much more detail in the video for learning outcome number 2 when we discussed the p-value method. So if you're curious about the distribution of x sub 1 bar minus x sub 2 bar and where all these distributions come from, I highly recommend that you watch video 9.2.2 to learn more about the background. In this video, we're just going to do an example using the critical value method. Now here is an outline for the procedure. Now I want you to notice that the first two slides for the procedure for the critical value method are exactly the same as the first two slides for the p-value method. So we start either hypothesis test in exactly the same way. First, we check the requirements for testing a claim about two means. Now, this procedure, which I'm about to outline for you, assumes that we do not know the population standard deviation of either population, and we're not assuming those are equal to each other. We could have a hypothesis test or conduct a hypothesis test if those were known, or if we were assuming that they were equal to each other. We're just not assuming that in this video. So it doesn't mean it can't be done, it just shouldn't be done using this method. So if those two population standard deviations are unknown and we have no reason to assume that they're equal to each other, and we have two independent samples, and both samples are simple random samples, and then either or both of these conditions are satisfied, so that both sample sizes are large, or both samples come from populations having normal distributions, then the requirements are met and we can use the critical value method to test that hypothesis. Now that last requirement just implies that the sampling distribution of the sample means, which was discussed in video 9.2.2, is approximately normally distributed. Okay, so once our requirements are met, then we need to write the claim in symbolic form and use it to infer the null and alternative hypotheses. That hasn't changed. It doesn't matter whether you're working with two means or one mean or two proportions or one proportion, you're always going to state the null and alternative hypotheses. And then you're going to use that information to, or not that information, you're going to use the information from the problem statement to identify or compute sample sizes, sample means, and sample standard deviations. And then to visualize what it is you're doing, I highly recommend that you graph a sampling distribution of x sub 1 bar minus x sub 2 bar, assuming that the null hypothesis is true, and then label that sample statistic x sub 1 bar minus x sub 2 bar from your sample data on the graph. That will help you visualize what it is you're doing. Remember, the question becomes, is x sub 1 bar minus x sub 2 bar significantly high or significantly low, given that the null hypothesis is true? In order to answer that, we compute the test statistic. And then here is where the critical value method and the p-value method that we talked about in the last video diverge. Well, actually, with both of those tests, you have to determine whether the test is two-tailed, left-tailed, or right-tailed, so we do that next. And then with the critical value method, you want to sketch and shade the critical region. So if it's a left-tailed test, you're going to shade a region on the left tail. If it's a right-tailed test, you're going to shade a region in the right tail. If it's two-tailed, you'll shade a region in both tails. And then there's going to be a cutoff value associated with that. Those cutoff values, those are values of the test statistic that separate values of the test statistic that are significantly high or significantly low from those that aren't considered significant in this context. Those are called the critical values of T. So you want to find those critical values. Again, those are just T scores that separate that critical region or critical regions from the area in the middle or from the rest of the area under the curve. Then once you have identified the critical values and you have sketched that critical region, you can make a decision about the null hypothesis. if you graph your test statistic on that graph and it lies in the critical region, then that test statistic corresponds to a value of x sub 1 bar minus x sub 2 bar that is either significantly high or significantly low value, or a significantly high value or a significantly low value. So, excuse me, in that case, we're going to reject the null hypothesis because something that was supposed to be rare is actually happening. So we will reject the assumption that led to us believing that this value is supposed to be rare. Now, if the test statistic does not lie in the critical region, then what we're saying is the value of x sub 1 bar minus x sub 2 bar from our sample is likely to occur given our assumption. So in that case, we don't accept the null hypothesis. We say that the null hypothesis might be true, so we fail to reject it. And then finally, we want to state our conclusion about the original claim in non-technical terms, because many people don't know what a null hypothesis is or an alternative hypothesis is. They don't know what an alpha value is or a p-value. They don't know what a critical value is, but they would understand some conclusion about the claim. So we want to state our answer, our final result, in terms that anyone can understand, even if they have not had a statistics class. Okay, so let's apply this. We're going to use the same problem statement and the same data that we used in the p-value method video. We're just going to use the critical value method instead. We're still using a 0.01 significance level and all of this data. So let me read the problem statement to you just in case you haven't watched that p-value method video in a while. The problem statement says, researchers from the University of British Columbia conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the same task. Responses were scored by a panel of judges, and results from scores of creativity are given below. And it looks like we've got sample sizes, and the bar is somehow missing. I don't know why, but that's supposed to be an X bar there. Those are sample means, and those are mean scores of creativity. And we've got sample standard deviations down here. And then it says higher scores correspond to more creativity, and researchers complain that the blue enhances performance on a creative task. Then we're asked to use the 0.01 significance level and the critical value method to test this claim. Then we're asked to identify the null hypothesis, the alternative hypothesis, the test statistic, and the critical values, and then state a conclusion about the null hypothesis as well as the final conclusion that addresses the original claim. In order to do this, the first thing that we'll do is check the requirements. So the values of the two population standard deviations are not known, and we have no reason to assume that they're equal to each other. The samples are independent, and we will assume that they are simple random samples. Now, the sample sizes were 35 and 36, so both sample sizes are large, which means that sampling distribution of the sample, each sample mean, is approximately normally distributed, which means that the distribution of the difference between the sample means is approximately normally distributed as well. Then we need to identify the null and alternative hypotheses. The claim was that blue enhances performance on a creative task. Now, in the little table that they gave us, let me show you. Red is designated as our first population, and the blue background folks were designated as our second population. So red is associated with a mean of mu sub 1, and this blue is associated with a mean of mu sub 2. So with that in mind, when they say that blue enhances performance on a creative task and our mean is a measurement of creativity, and they're saying larger values of the mean are associated with more creativity. If they're saying that blue enhances performance on a creative task, what they're saying is the mean for the blue group is greater than the mean for the red group. Now, since the blue group is our second population and the red group is our first population, that's the same as saying that mu sub 2 is greater than mu sub 1. Remember, those are population means. Now, that claim does not contain the condition of equality. So that makes it the alternative hypothesis. And typically, when we write that, we always write it with mu sub 1 first. So rather than saying that mu sub 2 is greater than mu sub 1, we're going to say that mu sub 1 is less than mu sub 2. That's our alternative hypothesis. That's the claim. And then if that's not true, the null hypothesis is, well, actually, we're not going to worry about whether or not that's not true. In order to come up with the null hypothesis, you just take this less than sign and you replace it with an equals sign. Okay, so we've got our null and alternative hypotheses. Then you either identify the sample sizes, sample means, and sample standard deviations or compute them. They were actually given to us in a summary table like this. When you do your homework over this material, sometimes they're actually going to give you the sample itself. Then you'll have to count all the values in your sample or use Excel to count them. That's going to be your N. You might have to compute the sample mean and sample standard deviation as well. So you can use technology like Excel to compute that sample mean and sample standard deviation, or you can do everything by hand. But I would highly recommend that you use technology to do that computation in order to save yourself some time. Now, if the sample sizes are small, you could do that by hand using the formulas from chapter 3, which you'll have access to during the exam. So during the exam, you won't have access to Excel, but you will have access to that table, and all your sample sizes will be either very small or the data will be given in summary statistics like this. So you won't have to do all of that computation. Okay, so we're asked to identify or compute these things, and we've already got them. We just had them in a summary table that was given to us. And then in order to make sure we understand what we're doing and why we're doing it, I always like to graph that sampling distribution of x sub 1 bar minus x sub 2 bar, assuming that the null hypothesis is true, and then label the sample statistic on our graph. The sample statistic on our that we're going to list on our graph is this x sub 1 bar minus x sub 2 bar from our two samples. Well, the first rating was 3.39. That was the rating of creativity for the first group. And then the 3.97 was the rating of creativity for the second group, which happened to be the blue group. And that difference is negative 0.58. So that is our best point estimate for the difference between mu sub 1 and mu sub 2. Now, when we're testing a hypothesis, we're assuming that mu sub 1 and mu sub 2 are equal to each other, which means that the mean of this distribution is equal to 0. And then we're saying to ourselves, if that mean is equal to 0, so if mu sub 1 and mu sub 2 are actually equal to each other, so it doesn't matter whether there's red in the background or blue in the background, the creativity ratings, the creativity means would be exactly the same. We're saying, is it statistically significant to have an x sub 1 bar minus x sub 2 bar that is negative 0.58? Is that significantly low? If it is significantly low, then we have a reason to throw out that null hypothesis or reject the null hypothesis. If it's not significantly high or low, then we'll say there's no reason to assume that the means are different from each other. Okay, so then we compute our test statistic corresponding to this difference, and our test statistic is given by this formula. Again, all that we're doing here is we are taking this distribution of x sub 1 bar minus x sub 2 bar, and we're converting it to a student t distribution, assuming that the null hypothesis is true. So we've got this expression right here. This mu sub 1 minus mu sub 2 is the mean of this distribution over here, which we're assuming to be 0 because the null is assumed to be true. And then the standard deviation is given by this, which is an approximation of the standard deviation of this distribution over here, where the population standard deviation sigma sub 1 and sigma sub 2 have been replaced by the sample standard deviations of s sub 1 and s sub 2. So you've got those plugged in, and that's over here. And then you've got this fraction over here. So you can simplify this. You can use your calculator to do that arithmetic, or you can use something like Excel, and then you'll get this answer over here. This is the same value of the test statistic that we computed in the first video over the p-value method. Now, this is the step. This next step is where the two values or the two methods diverge. With the critical value method, the next thing that you want to do after you compute that test statistic is you want to find the critical values. So you have to determine whether the test is two-tailed, left-tailed, or right-tailed. And to do that, we look at that alternative hypothesis. Since it has a less than sign, it's like an arrow pointing to the left. That's going to be a left-tailed test. And then in order to find the critical value, we need to know an estimate of the number of degrees of freedom. Now, you can use the exact value of degrees of freedom as we did with the p-value method, or you can just use the conservative estimate, which is that the degrees of freedom are given by the minimum of the two sample sizes, or one less than each of the two sample sizes. So you've got that first sample size -1 and the second sample size -1. Our first sample size was 35, so one less than that is 34. The second sample size was 36, one less than that is 35. The minimum of 35 and 34 is 34. So that is our conservative estimate of the number of degrees of freedom. And when we say conservative estimate, all we mean is that using this number of degrees of freedom will make it less likely that we reject the null hypothesis. Yes, I think that's right. If I'm wrong about that, please let me know. For some reason, I'm like questioning myself. Okay. Now, once you have that conservative estimate of the number of degrees of freedom, you can use it to find the critical value of t. And if we don't have access to technology, what I would recommend you do is identify alpha. And then since it's a left-tailed test, the area in the left tail is given or will be equal to our significance level alpha, which was given in the problem statement as 0.01. And then you would go to table A3, and in table A3, it will tell you the value of that critical value. Now, it doesn't include this negative sign, but the negative sign is implied because we're looking at a left-tailed test. Let's go to table A3 and I'll show you how to find this. Okay, so we have an area in one tail of 0.01. So we know we're in this second column right here. And to find the corresponding critical value, we're going to look for the number of degrees of freedom over here. Now, we have estimated that the number of degrees of freedom is 34. So we go to t equals 34. That's right here, and we're going to go to the second column. And that's giving us this value right here. But that value is always a positive value. All the values, the critical values in this table are positive. But you just multiply by -1 to get the critical value on the left side rather than on the right side. Since it's a left-tailed test, our critical value is going to be to the left of that mean in the student t distribution, and the mean is 0. So it's going to be a negative value. So t is -2.441, using that conservative estimate of the number of degrees of freedom, and remembering that we're dealing with a left-tailed test. Oops. So you get that -2.441 from the table. And then you say, okay, let's, so if we've got a left-tailed test, let's graph the critical region and the test statistic in it. So our critical t-value is -2.441. So that's right here approximately. And the test statistic that we computed earlier was approximately -2.98. So it's a little bit farther out in that left tail. So our critical region, it's actually this area right here. All of that area is the critical region. And our test statistic is in the critical region. It's right there at that value. So since the test statistic is in the critical region, we're going to say that that test statistic is significantly low, and that means that the x sub 1 bar minus x sub 2 bar that we have from our sample data is also significantly low. And if it's significantly low, what that just means is that it's highly improbable that that would happen given that the null hypothesis is true. So we're going to say, if it's highly improbable that it would happen given that the null hypothesis is true, but it actually happened, well, then the null hypothesis may not be true. Let's reject the null hypothesis. So we make our decision based on whether that test statistic is in the critical region or not. Since it's in the critical region, we can reject the null. Now, some students prefer to not think of this visually, but instead look at inequalities, look at the absolute value of the test statistic and the absolute value of the critical value of t, and then see which one is larger. So you could just take the absolute value of this, that 2.98, and take the absolute value of this, that 2.441, and see that this absolute value is greater than this absolute value. And what that means is that that 2.98 is farther away from t equals 0, which is in the middle, than the critical value of t. So it's farther out in that tail. I mean, that's what absolute value means. It's distance from 0. So if this distance from 0 is greater than this distance from 0, this means that the test statistic is farther out in the tail, which means that the test statistic is in the critical region, which means we're going to reject the null hypothesis. I actually prefer the graphical approach myself, but some people just prefer to learn rules like this. But remember that rule just corresponds to showing algebraically that the test statistic is in the critical region. So we're going to reject the null hypothesis. Now, after we decide that we're rejecting the null hypothesis, we need to state our conclusion in terms of the original claim. Now, our claim was that the first mean was less than the second mean. So when we reject the null hypothesis, we're actually supporting our claim. So we would say there is sufficient evidence to support the claim that blank. And you could say support the claim that mu sub 1 is less than mu sub 2, but we don't want to say that. We want to say it in terms everyone can understand. So we'd like to fill that claim right in. Our claim was that blue enhances performance on a creative task, having blue in the background. And it turns out with this data, there's sufficient evidence to support the claim that blue enhances performance on that creative task. So that's the critical value method. I will see you in the next video to discuss the confidence interval method. We'll discuss how to find a confidence interval estimate of a difference between two population means and when that's appropriate. And then we'll talk about testing a claim with two means with sample data collected from two independent samples using the confidence interval method. Again, we are assuming that the population standard deviations are unknown and not assumed to be equal to each other. And we'll discuss that in the next video.